Hi, I am Fasih Haider and I am a research fellow with the University of Edinburgh. Today I am going to talk about how can we monitor mental health through spontaneous speech. The emerging fields of social signal processing and effective computing seeks to build models to automatically characterize human behavior in interactive situations. This includes the detection of emotion and attitudes which can, among other things, influence communication effectiveness both in dialogue and in presentations. Methods developed in these fields have found application in the analysis of clinician patient communication, education, entertainment, and mental health monitoring. Currently, I am working on the SAM projects, and in that project, we are employing ambient assisted living technologies to analyze activities and health status, uh, which will provide personalized multimodal coaching to elderly person living on their own or in assisted care settings. Such activities and status include mobility, sleep, social activity, air quality, cardiovascular health, diet, and attitudes and emotions. Audio signal could have an application in SAM projects, as audio signal is used in a number of automatic prediction tasks, including cognitive state detection, presentation skill assessment, and emotion recognition, and also help in mental health monitoring in resource constraint settings such as using Raspberry Pi and microphone. But it brings privacy concerns of users such as spoken content of the user and their identity. We have proposed a data collection system to address the privacy to address the content privacy of user. Just to give the description of the hardware, like the hardware contains a matrix creator board. It consisting of a microphone array and inertial magma unit sensors and several other sensors like temperature and pressure. And we have a Raspberry Pi 3B plus. This setup is meant to be installed in room where social activity and dialogue instructions occur most frequently, such as dining room or a sitting room. And the software component here, there's two main components. One is voice activity detection. One is a acoustic feature extraction using OpenSmile. For voice activity detection, we employ the audio talk Python binding, and for acoustic feature extraction, we use OpenSmile toolkit. And we have also a user recognition module as used to process the audio file and save the speech feature in attribute relation to file to format. Um, just to give you some architecture information, like there's a live audio stream, and first from live audio stream we are detecting voice activity and saving the clips. As soon as there's a clip save, it will be processed for speaker recognition and also for feature extraction, and it saves the features and also delete the audio clip from original audio clip, and those features will be analyzed for effective emotional processing and cognitive decline detection. The feature set we used, the three kind of feature sets we used using OpenSmile. They have been widely used for emotion recognition, eating condition recognition, and cognitive state detection. Just to give you a brief description of those sets, one is a ammo base, one is a compare, and other one is EG maps. And the description of the features include in each feature set is listed on the slide. For more detail about these features, you can consult the references mentioned in the footnote. I'm just about to give you a system demonstration.
This is a demo of a real-time system for collecting data while preserving users' privacy for ambient-assisted living technologies. In this demo, audio segments are detected, and from them, OpenSmile features are extracted for user speech or other sounds. Other sounds will be placed in this folder, and user speech features will be placed in this folder. As the audio segments are created, they are analysed and then deleted for privacy reasons. We'll now run the system. As you can see, the running system generates segments which are then deleted once they are analysed. The OpenSmile features are currently being placed into the other folder as I am not the registered user of the system.
Yes, and our hardware contains Matros Creator and Raspberry Pi B plus 3. And you can see my features are placed in user folder because I am registered as a user.
Finally, if we open one of these folders, you can see the EEG maps OpenSmile features that are generated from the system.
We have used Pit Corpora, and we selected a subset of that. We have selected a subset from that Pit Corpora. Pit Corpora is about cookie theft description task, and these are the monologues. And the distribution of the gender and the age is shown in the table. When we apply voice activity detection on the audio recording of cookie theft description task, we got 2033 speech segments from 82 non-80 subjects and 2043 speech segments from 82 80 subjects. There are features that are correlated with the duration of speech segments. That's why we perform a Pearson correlation test so that to remove the features that are significantly correlated with duration, like R is greater than 0.2. As a result, we have 75 EG maps, 711 MO base, 3899 compare, and 4688 MRCG feature sets, which are not correlated with the duration of the speech chunks. And they are used for further machine learning experimentation. For the MRCG feature sets, you can consult with the reference below. We have conducted three kind of experiment. One is segment element, one is majority vote, and one is active data representation. For active data representation, you can consult the reference listed in the footnote. The segment level classification work at a segment level, classifying each segment separately. Then majority votes work for taking the majority vote of all the segments to distinguish one subject is AD or not. Now here are the results for segment level classification. We can see the segment level classification provide 56.55% accurate, and the majority vote is better than like 61.59% accuracy. When we use ADR, we can see that the LDA provide the best results, 77.44%, but the DT is more reliable and provides on average better results than all the other methods. So that we take the first top three results from the ADR using DT, and then fuse them, and it will increase the accuracy until 78.7%. Just to compare it with the previous approaches, like this study provides 78.7%, it is modality is acoustic and it's fully automated. The other approach is some of other approaches provide better results on Pit Corpora, and their results are not their approach is not fully automated. Like that, mostly people are using text, manually transcribed text, and getting an accuracy until 81.99%. To explore the emotional prosody for dementia, we first train a classifier using MODB datasets. MODB datasets is a dataset which is annotated for 6+1 emotions, and the language of that dataset is German. And we use EGMAS features for training the classifier for emotion recognition. And this is the confusion matrix of emotion recognition task, which has 69.72% accuracy in classifying 6+1 emotions. These emotions are anger, boredom, disgusting, fear, happiness, sadness, and neutral. Then we apply this classifier on the Pit Corpora speech segments, and we can see that there is we can see the emotions associated with the segments of pit corpora, and this is their distribution for AD and non-AD subjects, where we can see the sadness is more prominent in AD as compared to non-AD, and also the anger is more has more instance for non-AD than AD. Then we conduct a statistical test using ANOVA, and we can see that the score of each emotion is significantly different for anger, sadness, and disgusting. And we can see that the AD have more sadness and less anger score, and also have less disgusting score. Then we use ABR method. ABR is effective behavior representation and the segment level and majority vote. For effective behavior representation is the histogram representation of number of emotion and the number of emotion for each subject in an audio recording. For more further details, you can consult a footnote paper. And we can see that the majority vote provide 58.54% accurate result, and 59.76% results is provided by ABR. We have fused the top three results like 59.76, 58.54, and 57.93 for further analysis. And we can see that the fusion of those three results improve the results until the accuracy of 63.42%. Then we perform analysis, which is across cross corpora. For this experimentation, we use EGMAP feature sets only, and we use another dataset which is Carolina conversation collections. It contains 9354 dialogue instance from 80 conversation that belong to 30 participants in the AD groups, and the non-AD groups contains 7052 dialogue instance from 139 conversation that belong to 16 participants. And we have choose the subset of pit corpora which we reported previously, and the one difference between pit corpora and the Carolina is that the pit corpora are monologues and focus on cookie theft description task, while Carolina conversation collections are interviews and they are dialogues. For feature transfer learning, we use the ADR method. The results of feature transfer learning between PIT and Carolina conversation is reported in this table. You can see that PIT ADR represent where we train ADR using PIT dataset, and CCC ADR means where we train ADR using CCC dataset. M is a hyperparameter for ADR, and the PIT and CCC we can see that the best result provided by best transfer learning is observed 81.04% on CCC, but it results in a decrease in on the PIT dataset. On average, like if we have a look, like we can see that the CCC performs better than PIT, and the average performance of algorithms are better on CCC dataset. To get further insight, we plot the best results confusion matrix. Like this confusion matrix represent transfer learning from PIT to CC, where the accuracy we obtain is 84.78%, and if we look the other way around, like from CC to PIT data, then the accuracy is 70.73%. To conclude, we demonstrate the relevance of acoustic features and effective behavior of spontaneous speech for cognitive impairment detection, and we perform feature transfer learning between monologues and dialogues, and we have also demonstrated the machine learning methods which is operating on an automatically extracted voice feature provided accuracy of up to 78.7%, and our results improve on those from fully automated models. They also preserve the user spoken content privacy, and the PIT subset is made available through Dementia Bank. Some of our publications are here. for further readings. And finally, the acknowledgement goes to European Commission Horizon 2020 project, which is funded under Grant Agreement 769661 and is